Hello viewers, in today's class we are going to discuss some differential equations reducible to variable separable form, right? So here in this class we are going to solve two problems from this topic, that is differential equations reducible to variable separable form, right? So let us first quickly see the meaning of variable separable form of differential equations, right? See, sometimes we have an equation of this form, right? That is dy over dx is equal to f of x and g of y, right? uh, this is a differential equation in which we have dy over dx is equal to the product of say two functions of x and y, right? So f of x times g of y, right? So to solve these type of differential equations, what we do, we separate the variables, right? See, what we do, we write dy over g of y, and then we write f of x and dx, right? And then we integrate both sides, and c is the constant of integration, right? So this is a brief description of the variable separable form, right? So if we have a differential equation of this type, we separate the variables, that is we take x variable to one side and the y variable to the other side, and then we integrate both sides and we can get the solution, right? But in this lecture we are going to solve the equations of this type, that is if we have say dy over dx is equal to the function of f of ax plus by plus c, right? So if we have equations of this type, then how we can solve these type of differential equations, right? So let us start. So let us start with an example, that is if we have to solve this equation, say dy over dx is equal to 4x plus y plus 1 whole square, right? And see, this equation is similar to this one, right? So here we have dy over dx, and here we have f of ax plus by plus c, and see this expression is of this form, right? So what we will do in these type of differential equations, right? So if we make the square of this side, then we cannot separate the variables here, right? So here we cannot separate the variables, hence what we have to do will reduce these type of equations to the variable separable form by making a proper substitution, right? So what we will do here, will take say v is equal to 4x plus y plus 1, right? So whenever we come across with these type of differential equations, we simply take this term as v, right? And here what we will do, will differentiate both sides with respect to x, right? So here v is a function of both x and y, right? So we can write here v of x and y, right? So if we take the derivative of both sides with respect to x, then we'll get 4 times 1, the derivative of x is 1, and here we'll have dy over dx, and the derivative of 1 is equal to 0, right? So we have 4 plus dy over dx, right? So now from this equation we can write dy over dx is equal to dv over dx minus 4, right? And now what we will do, we'll take this value of dy over dx as dv over dx minus 4 over here, right? So we'll get dv over dx minus 4, and for 4x plus y plus 1 we can write v, right? So here we have v square. So now we can easily see from this equation that we can separate the variables, right? See, we can write it as dv over dx is equal to v square plus 4, right? And see, this function is a function of only v, right? So we can write it as f of v. So now this equation is reduced to the variable separable form of this type, right? So here we have f of v. So now we can separate the variables. It means we can write dv over f of v is equal to dx. And for f of v, we can now write v square plus 4, and here we have dx. Now we can integrate both sides. So we have dv over v square plus 4. Here we have integral of dx, and c is the constant of integration, right? And here we have got a very standard integral because we know that dx over x square plus a square is 1 over a and tan inverse of x over a, right? And see, here the variable is v, and for 4 we can write it as 2 square. So this integral is similar to this one. So now we can write 1 over a, that is 2, and here we have tan inverse v over 2, and integral of dx is x, and here we have c, right? Okay, now we can multiply both sides by 2, so we'll get tan inverse v over 2, that is, here we have 2x plus 2c, and now we can resubstitute the value of v as 4x plus y plus 1. So now we can write tan inverse of 4x plus y plus 1 over 2, and here we have 2x plus say c prime, right? Where c prime is some other constant, so c prime is equal to 2c. And now if we take this tan inverse to this side, so we'll get 4x plus y plus 1 over 2 is equal to tan of 2x plus c prime, right? And we can also write it like this, that is 4x plus y plus 1 is equal to 2 times tan inverse of 2x plus c prime, right? So now we can further express this result as y is equal to say minus 4x minus 1 plus 2 times tan inverse of 2x plus c prime, right? So now this side is completely expressed in terms of x, and here we have y, right? So this is the desired solution of this differential equation, right? So here we have seen how we can reduce these type of differential equations to variable separable form, right? So let us take one more example. So now here we have one more problem. So we have to solve here dy over dx plus 1 is equal to e raised to x plus y, right? And again this equation is of this form, so we can rewrite this equation as dy over dx is equal to e raised to x plus y minus 1, right? So now here our substitution would be v is equal to x plus y, right? So we'll take x plus y is equal to v, and now we can differentiate both sides with respect to x. So we'll have dv over dx is equal to 1 plus dy over dx, right? So here the derivative of x is 1. So now we can write dy over dx is equal to dv over dx minus 1, right? So now here we can replace dy over dx by dv over dx minus 1, right? So now we can write this equation as dv over dx minus 1, and here we have e raised to v minus 1, right? And now we can write dv over dx is equal to e raised to v minus 1, taking this negative 1 to this side, so we have plus 1. These two get cancelled, so we have e raised to v, right? And now see, we have dv over dx is equal to e raised to v, and see, this e raised to v is entirely a function of v, right? And we have now reduced this equation to the variable separable form, right? Because see, we can write dv over f of v is equal to dx, right? Now we can write this equation as dv over f of v. F of v is e raised to v, and here we have dx. Now we can integrate both sides, so we can have here this equation, right, where c is the constant of integration. Now we can write this integral as e raised to minus v dv, taking e raised to v to the numerator, and here we have integral of dx is x plus c, right? And the integral of e raised to minus v is minus e raised to minus v, and here we have x plus c, right? And again we can replace this v by x plus y, so here we have minus x plus y, and that is equal to x plus c, right? So this is the required equation, or the required solution of this differential equation, which has been reduced to the variable separable form. Now let us take one more example. So here we have to solve this equation, that is dy over dx is equal to cosine of x plus y, right? And again if we observe, this equation is of this form, right? So the right hand side is of this form, that is cos x plus y is of the form f of ax plus by plus c, right? So here a is 1, and b is also 1, and c is equal to 0, right, if we compare the right hand side, right? So here again we'll take the substitution, that is v is equal to x plus y, right? And differentiating both sides with respect to x, we'll get dv over dx is equal to 1 plus dy over dx. dy over dx can be written as dv over dx minus 1, right? So now this dy over dx can be replaced by this term, so we can now write dv over dx minus 1, and here we have cosine of v, right, because x plus y is equal to v, right? So now taking this negative 1 to this side, so we have dv over dx is equal to 1 plus cosine of v, right? And now see, this function is a function of v only, right? And we have got a variable separable form, right? So we can now separate the variable v and x, so we have dv over f of v, that is equal to dx, right? So now we can here write dv over f of v. F of v is 1 plus cosine of v, and here we have dx, right? So now we can integrate both sides, so we can write dv over 1 plus cos of v, and here we have integral of dx plus c, where c is the constant of integration. So now here we have an interesting integral, and see, here we have 1 plus cos of v, right? So here we'll make some trigonometric use of trigonometric identities. So what we will get, see, 1 plus cos theta is equal to 2 times of cos square theta over 2, right? So here we'll use the half angle formula. So 1 plus cos of v is equal to 2 times cos square v over 2, right? So this is an important trigonometric identity, and here we have x plus c, right? So now we can take half outside, and 1 over cos square v over 2 is the secant square v over 2 dv, right? And here we have x plus c, right? And again we have here a standard integral, and we know that the integral of secant square theta is equal to tan theta, right? So here we have v over 2 for the angle theta. So what we will write, will have half, and then we have tan v over 2 divided by half, right? So we'll divide the this tangent of v over 2 by the coefficient of v here, right, which is half. So here we have x plus c. Now this half and this half get cancelled, so we are left with tan v over 2, and here we have x plus c, right? So now here for this v, we can now write x plus y. So we can have tan of x plus y over 2 is equal to x plus c, right? And now if we take the inverse of tan inverse of both sides, we'll get x plus y over 2, and here we can write tan inverse of x plus c, right? And taking this 2 here, that is multiplying this term by 2, we can now write x plus y is equal to 2 times tan inverse of x plus c, and taking this x to this side, we can now write y is equal to 2 times tan inverse x plus c minus x, right? So viewers, the solution of this differential equation is given by y is equal to 2 times tan inverse x plus c minus x, right? And we can write this expression as y is equal to the function of x, right? So y is some function of x, right? So this is how we can solve these type of differential equations, which can be reduced to the variable separable form by making a proper substitution.